All right, let's jump right into this explainer. Today, we are bridging what feels like a massive gap between two wildly different worlds: the fast paced, hyperlogical realm of tech and the complex, deeply human world of clinical research. Look, if you're a developer, a data scientist, or just someone who naturally thinks in algorithms and systems, staring at medical literature can literally feel like trying to read a foreign language. You see terms like p-values and confidence intervals, and sure, you might think you know what they mean from your Stats 101 class, but clinical medicine applies them in incredibly specific, sometimes counterintuitive ways. So today, we're decoding the whole shebang. We're going to translate dense medical data into frameworks you actually already use, leveraging a curriculum built specifically for technical minds. Now, the beating heart of this curriculum, which takes a lot of inspiration from the Vibrown's framework, is a pretty profound shift in perspective. As tech folks, we're hardwired to want to jump straight into the numbers, right? Give us the data sets, the raw variables, let's get to work. But clinical cognition just doesn't work that way. It is fundamentally human-centric. Evidence-based medicine doesn't start in a spreadsheet. It starts with a patient sitting right in front of you in an exam room with a very specific history and a very specific problem. Once you anchor the statistics to a real human being, all those abstract numbers actually begin to make sense.
Okay, so here's our game plan for today. We're going to hit 5 main areas. 1. Medicine for the techie. 2. Translating the clinical jargon. 3. A deep dive spotlight on pooling the evidence. 4. Surprising insights in numbers. And 5. Utilizing the LLM research assistant.
Let's kick things off with Section 1, Medicine for the Techie. Normally, learning medicine means burying your head in massive 1,000-page textbooks. But this material employs a totally different methodology called guided discovery. It relies heavily on Socratic learning. Think of it kind of like interacting with an AI that actually questions you, rather than just spoon-feeding you the answers. For a non-medical learner, this is absolutely crucial. You aren't just memorizing random facts. You are actively building what we call a clinical cognition operating system right in your brain. Every single lesson builds on the last, taking you from a patient's clinical history to figuring out how to ask the right questions to ultimately judging the scientific evidence itself. Moving right along to Section 2, Translating the Clinical Jargon. Whenever you first look at clinical research, the jargon can seem really intimidating. But honestly, if you work in tech, you already speak this language. You just use different labels for it. A randomized controlled trial, or an RCT. That is literally just an A/B test run on human biology. Likelihood ratios and diagnostic testing, those are simply Bayesian updates, adjusting your prior probability based on incoming new data. And the grade framework, which clinicians use to build those big practice guidelines, that is exactly like weighing your test coverage against making a final ship decision in software development. Viewing the medical science through this familiar lens instantly demystifies it. It's a real game changer. And that brings us to Section 3, Spotlight on Pooling the Evidence. So if a single RCT is just an A/B test, then systematic reviews and meta-analyses are where we run a massive, complex SQL query across every A/B test ever done on a specific subject. This right here is the absolute peak of the evidence pyramid. Instead of relying on one single study, which, let's be real, might be flawed or too small or heavily biased, clinicians use systematic reviews to pull multiple trials together. This lets us zoom way out from the noise of individual studies and see the holistic, comprehensive view of the data. It is the ultimate signal-to-noise filter in medicine. But here's the catch. You can't just blindly mash a bunch of data sets together and hope for the best. You have to treat this like a rigorous data science problem. Clinicians use specific visual tools called forest plots to line up studies side by side. They measure heterogeneity, they hunt for publication bias using funnel plots, and they grade the whole review's quality using a really strict framework called AmStar2. Let's actually break a few of these concepts down because understanding the specific appraisal workflow is absolutely essential for validating any clinical data. First up, we've got heterogeneity, which is quantified by an index called I-squared. Think about it. When you pool data from 5 different clinical trials across the globe, they aren't going to be perfectly identical. Maybe one trial used a slightly older demographic or a slightly different dosage of a drug. I-squared measures the variance and consistency between all these studies. If that I-squared percentage gets too high, well, it means you are basically combining apples with oranges. Your pooled data just became meaningless. As a techie, you can think of this as checking the structural consistency of disparate databases before you try to merge them. Then we have funnel plots. I love these because they are a remarkably clever visual tool used to spot what isn't there. You see, in academia, positive results get published way more often than negative results. This is known as publication bias. A funnel plot maps out the size of a study against its results. In a perfect, unbiased world, the data points should form this nice, symmetrical, inverted funnel. But if there's a huge empty chunk missing from one side of the funnel, that strongly suggests that smaller studies with negative results were quietly stuffed into a desk drawer and never published. It acts as this crucial stress test for the validity of our meta-analysis. If the funnel plot is skewed, the pooled evidence you're looking at might just be a complete illusion.
All right, Section 4, Surprising Insights and Numbers.
Here is a super counterintuitive insight for you. You might have just 5 individual trials that are completely underpowered on their own, meaning they just don't have enough participants to prove statistical significance. But thanks to the magic of meta-analysis, when you pool those 5 underpowered trials together, they can magically add up to a highly confident, definitive clinical answer. Or consider the concept of NNT, the number needed to treat. This one will bend your mind a bit. Let's say you read a flashy news headline claiming a new drug offers a 40% risk reduction for heart attacks. That sounds massive, right? You'd want that drug for sure. But that is usually just the relative risk reduction. When you run the math on the absolute numbers, you might find an NNT of 25. What does that mean? It means a clinician actually has to treat 25 different people with this drug just to prevent one single heart attack, while the other 24 people get 0 benefit and still have to risk the side effects. It literally completely changes how you view a medical headline. And how about this? The exact same diagnostic test with the exact same chemical accuracy in a lab can have wildly different real-world value depending entirely on who you test. If you use a test on a population where a disease is incredibly rare, the positive predictive value might only be 8%, meaning almost all of your positive results are actually false positives. But if you take that exact same test to a specialized clinic where the baseline prevalence of the disease is high, suddenly its predictive value jumps to 90%. Baseline prevalence dramatically alters a test's usefulness, which perfectly ties right back to that Bayesian updates concept we talked about earlier. Finally, let's hit Section 5, the LLM Research Assistant. So how do we actually do all this? Well, it all builds into a complete AI-assisted workflow. The curriculum provides a prompt library to help you at literally every stage of breaking down a clinical paper. You can use an LLM to formulate your initial clinical question, which is known as a PICO question. You can use it to build complex Boolean search strategies for PubMed. You can have it screen abstracts, extract the trial methodology, and yes, even calculate those tricky absolute risk and NNT stats we just talked about. It can even stress test your own appraisal of the evidence. But, and this is a massive, absolutely critical but, here is the golden rule you have to follow. The LMM drafts, you verify every number and citation against the source. The LMM is just a research assistant. It is not a source of absolute truth. We all know that AI can hallucinate. But in clinical medicine, a hallucinated number isn't just a software bug. It could result in real physical harm. Rigorous manual verification of the LMM's output against the original medical paper is absolutely non-negotiable. Which brings us full circle to the culmination of the course, where you run a real de-identified patient case through this exact end-to-end framework. You start with their history, you form that PICO question, you run the search, you appraise the meta-analyses and check those funnel plots. And finally, you make an informed clinical decision. You've successfully moved all the way from raw data to applied human care. We've covered a ton of ground in this explainer today, translating the rigorous world of evidence-based medicine into a framework that any techie can understand and actually use. So I'll leave you with this final thought. Armed with these first principles, an understanding of how to actually pool and appraise data, and a suite of LLM prompts, how will you decode the clinical evidence the next time you or a loved one face a complex medical decision? The tools are now in your hands. Thanks for joining me and happy researching.